lab that we did, as well as your iPad opened up to this lab where we actually manipulated the frequency and we measured the wavelength. The other thing that you did was you looked at wave speed. Now, when you take a look at this, before we even get into some of the numbers, you see your frequency is down at the bottom as 1.5 hertz. So I'm just going to increase that frequency. And as I increase the frequency to 3, that'll make it the highest, you can see that the oscillator is going faster. And we can also see that the wavelengths are much smaller. So increasing your frequency decreases your wavelength. Decreasing your frequency increases your wavelength. Now, we knew that pattern before we even went into this lab, but what we wanted to do was figure out if there was some kind of mathematical pattern that you could determine. So go ahead and take a look at your numbers. There was no requirement on what frequencies you chose. I asked for you to start off as 1.2, and when we measured the frequency at 1.2 and the wavelength was 5.2 centimeters. Okay. We also know that they had to get bigger. So I'm just going to use some sample data of one of my other students. They chose a frequency of 1.3 and they got a wavelength of 4.8. Increasing the frequency, decrease the wavelength. They chose a frequency of 1.4 and they got a wavelength of around 4.5. Again, same pattern. 1.5, 4.3, and 1.6, 4.0. Now, you check your frequencies and your wavelengths with the person you're sitting next to. You should have seen this pattern, and that pattern tells you that increasing your frequency, so when your frequency increases, then your wavelength will decrease, and vice versa. Now, if you think about what type of relationship that is an inverse relationship. If you remember, inverse means when one variable goes up, the other one would do the opposite, so it would go down, or vice versa. If the frequency decreases, the wavelength would increase. So you should have made a wavelength frequency graph, and it would have been rather linear, starting up top with a negative slope that looked like that, okay? Now, the other thing that we wanted to do was a quick comparison with the wave speed. Now, if you'll notice, on my FET site, I did nothing to the string at all. I didn't change the tension. I didn't change the medium. If you remember, when we had a high tension, we ended up usually getting about a 6.2 centimeters per second. Or in the ballpark was also 6.4 centimeters per second, and so on. Now, some of you might have taken the time to calculate every single wave speed. Every single wave speed should have been this. If you were not getting in the 6-ish range, then you were messing something up. Because the only way that I can change my wave speed is if I change my medium. All right, so if I don't change my medium, then my wave speed is never going to change. So that is an important big idea. We saw that with the pulse big ideas. We're revisiting it here with the waves as well. Now, what I asked you to do was to kind of see what you notice about a pattern. And that pattern being, how do you think frequency and wavelength connect to wave speed? So if you were to take a minute and just multiply frequency times wavelength for every single one, frequency times wavelength, frequency times wavelength. When you do that, you are going to end up with wave speed. It's an alternate way that you can come up with wave speed. Some of you might have seen that pattern, some of you might not have. Again, if the substitute needs to pause the video just so that you can do this quick calculation, feel free to do that. Now, what we want to do is, if we can establish some patterns, we now want to kind of put those together on our big idea sheet. So go ahead and open up your lab notebook. You want to open it to your waves, big ideas section. And remember, everything that we are coming up with for big ideas are essential information. You're going to need to know that for the test that you take next class. Now, if we take a look at our waves, big idea, let's just revisit where we've been. First thing that we know is that you have to add energy to your medium in order for there to be a pulse or a wave. If you don't add energy to the medium, then you're not going to have any of that. We also know that the energy is what's moving. The medium does not move. Now, the medium might wiggle just a little bit, but it's not going to have an overall net movement. Lastly, we know that energy can travel through different mediums. And we also now know that when you change the medium, you're definitely going to change the speed of it as well. Now, when we did the pulse labs with the snaky and the slinky, these pulse big ideas are also apply to waves. And so you could use this as pulse or wave, but the lab was actually around pulses. So one pulse has a constant speed in a medium. That pulse is never going to speed up. That pulse will never slow down unless I change my medium. I know that amplitude affects how tall my pulse is or how much energy there is, but it does not affect speed. I know that damping affects how long the energy stays in the medium, but it does not affect speed. The one thing that affects speed is the tension. So when you increase your speed, you're going to increase your tension. So this brings me to my frequency wavelength connection. Now, obviously, frequency and wavelength are only going to work with waves because you don't have a frequency if you have a pulse. You don't have a wavelength if you have a pulse. But the idea being that when you increase your frequency, then you will decrease your wavelength. The one thing that's important here is that you understand that the wave speed is constant. It's never going to change unless I change my medium. So as you can see, I've drawn over to the side a low frequency on top with a very long wavelength and a high frequency on bottom with a very short wavelength. Understanding these patterns leads us to being able to do calculations. So as soon as everyone is ready, we're going to open up to our formulas page. Substitute, just pause the video if you need to. All right, go ahead and find your formulas page. We've not done anything with waves yet, so let's go ahead and add on our first formula. Now, anytime we do calculations, we have symbols that represent different things. We also have units that are corresponding to those particular variables. So if you'll notice, I'm saying wave speed. V stands for wave speed. Notice there's no vector across the top. The symbol for wave speed is a V. We have wavelength, and then we have delta T. Now, delta T stands for time. So let's come over here and write wave speed, wavelength, and time. Wave speed is typically going to be measured in meters per second. That's going to come up in a game you're going to play in a little bit. Wavelength is typically measured in meters, and time is typically measured in seconds here. So when we do our game, you'll always want to make sure your units are meters per second, meters, and second. Now, if I wanted to find my wave speed an alternate way, another way you could find wave speed is by taking frequency and multiplying it times wavelength. Frequency times wavelength will also give you wave speed, so depending on what information you've been given. So let's add frequency over to this side. Now, if you remember, frequency has a unit called a hertz. Hertz is simply cycles per second, and that's what they call that. Now, if I wanted to, I could take this equation that I just wrote, wave speed equals frequency times wavelength, and I could just algebraically manipulate that, and I could solve for frequency. So if I want to solve for frequency, I've got to send wavelength over to the other side, so it would be wave speed divided by wavelength. And if I wanted to solve for wavelength, I could do that. I would just have to send frequency over to the other side, and it would be wave speed divided by frequency. Now, you're going to get some practice with these formulas. The one thing that's important is anytime you do calculations, you need to show your work, show your units, and show what formula you're using. So the substitute is going to explain how we're going to do a game. We'll do an example first so you understand how it works, and then you'll be able to run through several example calculations.